Hi, welcome to Complex Analysis. This is the second session on the extended complex plane. In the last session, we introduced an extra point called point at infinity to the complex plane, and the resulting space we called extended complex plane, and we equipped a topology on that. We especially told what are the open sets and basic open sets around infinity in this space, and we also looked at continuous functions, functions from C infinity to C which are continuous at infinity, some examples. So now we want to look at few more examples, and you will learn what really happens there and formulate it, and then move on to defining what are holomorphic functions on such spaces. Okay, stay tuned, we will be ready. So suppose F why it's happening. Suppose F is a polynomial, non-constant polynomial, n is not equal to 0 and n is greater than or equal to 1. Right? I want to know, can we define f infinity, a complex number, so that f is continuous at infinity, right? So let us assume f infinity equal to alpha, a complex number, right? I want to check continuity of f at infinity, therefore let epsilon be given. So let me look at epsilon. This is b alpha epsilon, right? Therefore if f is continuous with this definition of f infinity, right, then there exists an open set, in fact a basic open set, call it un, so that f of un is contained in b alpha epsilon, right? There should exist a neighborhood of infinity, it gets mapped to this open set, right? Okay, now let us recall f is a polynomial, therefore we know the following result. Okay, recall the following fact. We know that f of z is greater than or equal to half of mod a n z power n for mod z very large. Okay, but let's not worry about the observation we need is the following. Given m positive, there exists r positive, so that mod z greater than r implies mod of f of z is greater than m. Okay, this is same as saying, if you learn analysis from me, this is same as saying mod f z goes to infinity as mod z goes to infinity. This can be defined with our context. I will come to that later. Is this clear? So I am going to assume this fact, right? Now let's look at, see, if I start with any w in b alpha epsilon, I can as well assume epsilon is 0 less than 1, right? Therefore mod w will be mod w minus alpha plus mod alpha less than or equal to, therefore less than or equal to mod alpha plus 1, right? Okay, but okay, now let us take m equal to 1 plus mod alpha. Therefore there exists an r positive, so that mod z greater than r implies mod of f of z is greater than m, right? Now choose a natural number n, okay, which is greater than maximum of r as well as this n. What is this n? This is the basic open set un, which had this property, right? Then notice that u of n is contained in u of n, right? Because what is u of n? U of n is c minus b 0 n union infinity, right? And b 0 n is contained in b0 capital N, etc., etc., right? This is clear, right? Therefore, what happens? Therefore, for every z here, what should I have? Mod fz should be greater than m, which is 1 plus mod alpha. But un is contained in u small n, that means for every z in this, mod fz should be less than m. This is 1 plus mod alpha, a contradiction. Yeah, pause, review, proceed. So what have we concluded? We have shown that if f is a non-constant polynomial function, it's not going to be continuous at infinity, right? Okay, maybe you may think that we used only this property, namely this one. This fact is what we used. This is used as a very crucial fact, right? So you may think that is the reason why, but let's look at something else. This is example 2. Let us look at f of z equal to e power z. Okay, so can we define finite infinity in C so that f is continuous at infinity? Now notice that when my z is of the form e power it, then mod fz is always 1. But whereas my z is a natural number like this, okay, mod fz is just e power n that goes to infinity. You understand? So still we have a problem. Why? What is the problem? Suppose as again f of infinity equal to alpha and put epsilon less than 1. It's not necessary, I am assuming that b alpha epsilon, there exists un, so that f of un is contained in this, right? Now I have a contradiction. Yes, right? What is the contradiction? So if n is very large, then okay, e power n will be greater than n. In fact, e power n will be greater than n itself. Yeah, that's good enough. Yeah, you understand that? E power n will be greater than n. So are you following? Yes. Now what is the problem? The problem is, suppose z belongs to un, then what does it mean? Mod z is greater than n, right? Z may be infinity, z is infinity, or mod z is greater than n, right? Therefore, what do I have then? Therefore, in particular, if I take n plus 1, that belongs to un, right? Therefore, if I take en plus 1, that is e power n into e, that is greater than e power n, that is greater than n. Okay, so a contradiction. So, okay, e power z is not continuous at infinity. When I say it's not continuous at infinity, remember e power infinity is not defined. What you are saying is we cannot extend e power z or polynomial as a continuous function to all of c infinity. Okay, the correct way of saying is this. A precise way of saying this is, okay, non-constant polynomial function or the exponential function okay cannot be extended to a continuous function on all of c infinity. That means I cannot define f of infinity properly. Okay, and remember, f of infinity want to be a complex number. We use that fact. Okay, please understand. This kind of subtlety may not people explain again and again. You may think there is something some difficulty. No, it's not difficulty. What all I am saying is, when I want to define f of infinity, I want it to be a complex number. Okay, so go through the proof. Do you understand what really happened? Suppose f is defined some neighborhood u. Okay, u is open. Okay, is open neighborhood of infinity, and suppose f is continuous at infinity. Right? So what can he conclude? If you look at this, the same thing, if f of infinity is some alpha, right? If I take epsilon as usual 0 less than 1, then I know there exists a neighborhood un so that f of un is contained in b alpha epsilon. That means for every z in un, modulus fz is less than 1 plus mod alpha. Yeah, the last two examples exactly show this. So there is a necessary condition. What is the necessary condition? If I have a function if I have a function f defined on open neighborhood of infinity to C, and if it is continuous at infinity, then f should be bounded on something. That is same as saying, so a necessary condition, f must be bounded for large values of z. Right? Whenever some mod z is greater than or equal to r, then I want to say mod z of z is less than or equal to something. And you understand this? Please try to understand. So this is a necessary condition. Now go back to the last example, two examples. In fact, if I have any non-constant entire function, okay, then there is no way I can extend it to a continuous function on all of C infinity. This as an immediate corollary we get that. So as a corollary, okay, let f from C to C be non-constant entire function, then f cannot be extended to a continuous function g from C infinity to C such that g restricted to C is f. That is, I cannot define f infinity as a complex number such that f becomes continuous at infinity. Why? This is by Leibniz's theorem. Okay. Do you understand why? Yeah. Let us go through the proof. This is how you will learn how to work with point at infinity, the topology around that. Okay, what are the open sets, and also various results from complex analysis. Right? How will I use this? So again, let us assume there is a g. Okay, let me simply say f of infinity is alpha as usual. I will denote f by g, and g infinity I will call it f infinity. Okay, I will define f infinity to be the value of g at infinity. Therefore, that's a function. Right? Now what do I know? Yeah. So what I know, the Leibniz theorem, what does it say? Since f is non-constant entire, f is not bounded. So what does that mean? If I say f is not bounded, okay, what does it mean? That means given any m positive, there exists a z in C such that mod fz is greater than m. Right? Because if f is bounded, what does it mean? So this is the negation of the statement. F is bounded on C would mean there exists M positive, so that for all Z in C, mod Fz is less than or equal to M. Okay. So what is the negation? Okay. For every M positive, I can find one complex number Z so that mod Fz is greater than M. Okay. This is a negation. Please understand. That is why if you have not gone through my foundation course, there are only 4 videos. Please go through them. Okay. I have found that even PhD students have problem with this kind of negation. This is my experience. Anyway. Okay. Is this clear now? Very good. Now let's see. Now as usual, let us look at my epsilon 0 less than epsilon less than 1. Let M equal to mod of alpha plus 1, where alpha is F infinity. Right. Now I know I want to claim there exists. Suppose F is continuous. So let's assume F is continuous at infinity. As usual, there exists un such that F of un is contained in B alpha epsilon. Right. Now you claim there exists Z in U, so un such that mod F of Z is greater than M. Because this, I know there exists some Z, I want to say there exists Z in un. Do you understand the difference? Look at this. What is the difference between these two sentences? Let's look at this sentence, and let us look at this sentence. What it said is there exists some Z in C, but now I know for every Z in un, okay, mod F of Z is less than F of Z belong to B alpha epsilon, therefore mod Fz is less than 1 plus mod alpha, that is M. But now I want to claim, because of Liouville's theorem, there exists already a U in this. Now how do I prove it? Okay. How do I prove there exists Z in un? Suppose not, then for every Z in un, mod Fz is less than or equal to M. Right. Now what is un complement? That is B0n. Right. Now this is compact and F is entire, right, and hence continuous. Therefore hence F is bounded on B01 because it's a compact set. That means mod F is, there exists M1 so that for all Z in B0n, mod Fz is less than or equal to M1. Right. That means for every Z in C, mod Fz is less than either. Okay. Now C is what? B0n union C minus B0n, right? Complement. And this fellow is contained in un. So if given Z has to be either here or Z here. If Z is here, mod Fz is less than M1. If Z is here, mod Fz is less than capital M. Therefore this is less than or equal to maximum of capital M and M1. But remember, F is an entire function which is bounded, therefore that means F is a constant. Okay. So this contradicts our hypothesis. F is non-constant, right? So pause, review, proceed. Okay. I hope this discussion helps you to understand lot of things, because typically in complex analysis courses, point at infinity is just given a very cursory thing. one line thing. When do you say f is analytic at infinity? That's a word they use. Even though I will use holomorphic. Okay, and second, residue at infinity someplace. Okay, and the other thing is Riemann sphere. Okay, these are the places where you use. Students are always sorry, uncomfortable how to work with. Okay, how to deal with point at infinity, the function's behavior at point at infinity, etc. That's why I give lot of examples and went through slowly. Please understand, go through this. You will see, you will be very comfortable and confident about this concept. Okay, now the next step is, suppose I have a function f which is defined on an open set containing infinity, taking values in complex numbers. I want to know whether f is holomorphic on U. Remember, U is an open set containing infinity. That means I want to talk about f is holomorphic in. Okay, f is differentiable at infinity. Okay, that means f is differentiable on the end, each and every point of U, and hence it's also differentiable at the point infinity. Do you understand this? Yeah. But before going, we will do a preliminary work. Okay, this will help us. Yeah, now we want to talk about holomorphic functions defined on an open set containing infinity. So let U be open set infinity. Okay, and f be a function from U to C. I want to talk about when I say f is holomorphic on U. Okay, but before that, let us look at a preliminary that will help us. Okay, so notice that we are going to talk about only differentiability. I will come to that. Okay, suppose U open set. Okay, and V also open sets in C, right? And suppose 5 from U to V is a bijection, and 5 from U to V is holomorphic, and phi inverse from V to U is also holomorphic. So in some sense, phi is a holomorphic isomorphism. See, because holomorphic functions are continuous, therefore phi becomes homeomorphism, right? And it's also holomorphic on each way, so it's some kind of an isomorphism in complex analysis. So this is something like an isomorphism in complex analysis, right? Okay, now let us look at let us keep pictures clear. Maybe I will write 5 from okay, B and U. Okay, there is a reason. Phi is now from B to U. Okay, now suppose I have this. This is my V. This is my U. This is a isomorphism of this open sets, holomorphic isomorphism. That is holomorphic homeomorphisms, or whatever you want to call it. Now this is a function f to C, right? Now fix a point A, right? I want to know when f is differentiable at A. Okay, remember we did something about continuity, right? I am trying to establish the same principle for differentiability in complex analysis. Okay, do you remember what we did? We had something like x to y to z and f, and this y, continuity of f at y is same as, let us call this phi homeomorphism. This is the composite f composite phi, right? That's why I wanted this way. So f is continuous at y if and only if f is continuous at x, that is at phi inverse of y. If and only if f composite phi. Okay, so So what should be the analog? I want to say f is differentiable at a if and only if f composite phi is differentiable at which point? So this will be a point which will be phi inverse of a is differentiable at phi inverse of a. Okay, this is the observation or the principle. Okay, the proof is extremely easy. Why? If f is differentiable at a, then f composite phi is differentiable by chain rule, right? At which point? Pi inverse a, whatever the point which corresponded to this, right? Yes, okay. So, and conversely, suppose f composite phi is differentiable at phi inverse a, then f of a, you see that f of phi, okay, composite phi inverse at phi a. Right, that is, let us look at f composite phi is differentiable, and I know is phi is differentiable. F composite phi is differentiable at what point? Phi inverse a, right? And phi inverse is differentiable where? Phi inverse, where does it go from here to where? At a, differentiable at a, right? Therefore the composite f composite phi inverse, that is f, is differentiable at a, again by chain rule. Yeah, do you follow that? Remember, what does the chain rule say? F is differentiable at a and g is differentiable at b, where b is f of a. Therefore g composite f is differentiable at a, right? That's what we are using. Okay, make sure, please understand. So I want to use this principle in the very special case. Okay, as follows. Okay, let us look at U to be an open set in C star. Okay, this is open. Okay, let be, this may be the map C from C star to C star, where phi of z is 1 by z. Then we know phi is a bijective and phi equal to phi inverse, and phi therefore is a holomorphic homeomorphism. Simply call it isomorphism so that it will be easier. Alright, in the complex analysis case, that's isomorphism. Is that okay? Now suppose I have a point A in U, then I want to say U. So let us look at, let V be equal to phi of A. This is my B in C star, and this is my U again in C star, and okay, phi of U. Okay, I have point A, this is F to C, and then I have composite. Right, so therefore f composite phi is differentiable at a if only if, sorry, f is differentiable at a if only if f composite phi is differentiable at phi of a. Right, now is this clear? The principle says this. Now try to understand. Okay, what is the function f composite phi of z? That is f of phi of z, that is f of 1 by z. And what is phi of a? Therefore f composite, the function z going to f of 1 by z is differentiable at phi of a, which is same as saying 1 by a. Do you understand this? Pause, review, proceed. Okay, if you understood this, now we are ready. Suppose U is an open set containing infinity, right? Yeah. Now I have the map phi from C infinity minus 0 to C star by C, right? What is that map? Z going to 1 by Z if Z is not equal to infinity, and infinity goes to 0. So, right? So, are you following? So I am going to say, therefore, F from U to C is differentiable at infinity if and only if F composite phi is differentiable at 0. But what is F composite phi? F composite phi at Z is F of 1 by Z. Therefore, the map Z going to F of 1 by Z is differentiable at 0. Okay, do you understand this? So notice that I have defined only the notion of differentiability. I am not talking about derivative. Even in the earlier case, I do not talk about derivative. Okay, of course chain rule will give me how to relate them, but that's not my aim. We are only worried about qualitative thing at present, differentiability or not differentiability. So we have said this. Is this clear? Now when do I say F is holomorphic? So when do I say this holomorphic on U? So that means F is, okay, that is F is differentiable at each point in U, right? But I claim this is same as saying, let us look at phi of U. Okay, that will be a map in C now, right? Because infinity will go to 0, other points will go to some points in C star. Do you understand that? Yeah. So I have, this is my infinity. Okay. So anything outside this is open set, right? Okay. These are the neighborhood of this. So where does it go? It goes to some neighborhood of 0. This is my phi of U. Remember, phi is a homomorphism, therefore that will be an open neighborhood of 0, because phi maps infinity to 0, right? Therefore I have a function. So I want to talk about that function. Okay, now what does it mean? I have a function Z here. Where does it go to? It goes to F of 1 by Z. It doesn't go to F of Z. Do you remember that? Go back. This is your phi. Therefore what I am doing? F composite phi must be differentiable at 0. Okay, right? So this map, this function should be differentiable. So let's look at example. There is a subtle point. I'll come to that in a minute. Okay. So no non-constant entire function will be holomorphic on U where U is open set containing infinity. Why? Because we have seen, okay, if it's going to be holomorphic, okay, it's going to be continuous. But we know, okay, if a function is continuous on an open set containing infinity, then it should be bounded for large values of mod z. Okay, therefore none of these functions will be. But let's look at this function f of z equal to z power minus n, where n is greater than or equal to 1. Okay, and where is z? And z is in u, which is c star union infinity. This is an open set, right? Now, is this differentiable? Is f differentiable at infinity? How do I know that? Let's look at what should I do. Where does it go to? Phi of u, what will be? C star will remain C star. Okay, union infinity will go to 0. Therefore, it is actually C. Alright. Now, what is the function I have to look at? I have to look at the function f composite phi from phi of u to C. That is f composite phi of any z is f of 1 by z. I want to know this is continuous at 0. But what is f composite phi of z? F of phi of z is 1 by z, and f of z is z minus to the power n, which is minus n, which is z to the power n. This is holomorphic at 0. Hence, f is differentiable at infinity. So, as an immediate corollary, any finite linear combination okay, this will be differentiable at infinity. Okay, right. Now, what is the subtle point? Suppose u is not equal to c infinity, and infinity, right, belongs to this, right? Then, and suppose z is not equal to infinity and z belong to u. Then you see that z belong to C star, right? Therefore, f differentiable at z, okay, but this is same as saying f composite phi differentiable at phi of z, that is at 1 by z. Are you following? So, again, let's look at the picture. This is my compact thing, and this is my point at infinity. Suppose I have z here, then differentiability of f at z, okay, can be defined in two ways. One is, since z is in C star, okay, then different, okay, the standard way. The other one, let's look at f composite phi, okay, because this is u, and therefore phi of u, that will be something in C, right? Phi of u, okay, differentiability of phi of u, phi f composite phi at phi of z. Okay, and what we know from our working principle is these are one and the same. Okay, our principle says these two ways are equivalent. What does it mean? Differentiability with respect to the first standard way is if and only if it is differentiable with respect to the second way using our principle, the map phi. Please understand, this will be, I know I am pushing you a little far because I am trying to prepare you for the study of manifolds and for the study of Riemann surfaces, etc. Okay, so this is a very good point of this. Let me stop here, and I thought at this I will give only 2 lectures on this, but there may be something extra I would like to say. Okay, let us do that now itself. It's better that I finish it, even if it's slightly longer. You can always pause it and review, come back. Now I can ask, what are the holomorphic function? Okay, C infinity, that is C valued holomorphic functions. That is function f from C infinity to C and holomorphic. I think the answer should be easy for all of you, right? Why? If f is holomorphic on C infinity, then f is to C, that is C to C is holomorphic. Therefore it becomes an entire function, right? But remember, if f from C infinity to C is holomorphic, then f from C infinity to C is continuous, right? And this is compact. Therefore f of C infinity is compact set. That means this is bounded. That means f is bounded, okay, on C infinity, and hence f is bounded on C, but it's the entire function. Therefore what do I conclude? F is a constant. Okay, so if I feel like I'll have a third lecture on this series where I will prove why C infinity is compact, and I'll also say why I looked at 2 ways of defining differentiability of a function f on C star. Okay, and how does something like a concept of manifold, etc., come into the picture. If you want to go for higher studies, learn a lot more topology and geometry or algebraic or differential, whatever, it will be worth your while. Okay, but those who don't want, you can simply stuck to what I said. F is differentiable at infinity if only if f composite phi is differentiable at pi of infinity, which is 0. Okay, and with that I gave already 2 examples. What are the 2 examples I gave? Anything of the form z to the power minus n, where n is natural number, okay, that is going to be differentiable at infinity. And then the only holomorphic function which are different holomorphic function on C infinity are constant functions. Okay, and okay, so please go through these things, and it may be challenging because this is not the, as I said, it's one line. Okay, f is differentiable if f of 1 by z is differentiable at z equal to 0. Okay, this is the standard thing, and not a, but we had looked at it lot more inward. We also related to homeomorphisms, topology. These concepts actually build the ground for defining a manifold structure. Okay, as I said, if I feel like, if I am in the correct mode, there will be a sequel to this. Otherwise this is good enough for whatever standard complex analysis course is concerned. I hope all of you enjoyed, even though struggled a bit. Okay, we will meet again. Take care and stay safe.